So we have different material properties I have listed below. First one, we call it as a elasticity. So elasticity is a property where a material will come to its original shape. So all material will have elastic properties, right? So when I consider a steel, even steel will have elastic property. So, but when you consider a part, so very important, more elastic part is a rubber band. If I consider a rubber band, so when I pull my rubber band, it will expand. When I release my force, again it comes to its original position. So this property we call it as a elastic property, right? Even if you consider a steel chair, so if you sit on a steel chair, you can able to see that there will be a small deformation which you can't able to identify. It will be in microns, right? But what happens is when you release that force, so automatically it comes to its original position, right? So all material will have elastic properties. The next one is plasticity. So any material which does not return to its original shape, that we call it as a plastic property material, right? So it is like all materials again. So it is also same. So same concept. All material will have plastic stage also. It depends on amount of force you are applying. For example, same rubber band, let me take. You are expanding continuously. At a particular stage, your rubber band won't come to its original position. So when I say original position, it means the real amount of dimension it has before and after applying load. So if my rubber band is 10 mm, if I apply a large amount of force, right, and if I release it, the rubber band won't be 10 mm. It may be 12 mm or 13 mm, which means a 3 mm deformation, extra deformation, right? So this stage we call it as a plastic stage, and that property we call it as a plasticity property, right? All materials will have these two properties. One is elasticity, other one is plasticity. So when you apply a small amount of force, you have elastic property. When you apply more force, then it goes to plastic property. So this can be very much defined and explained better in a stress strain diagram. So you can able to see that. We will discuss it later, right? So the next one is ductility. So ductility is a material which can be stretched to a wire without any crack. If I consider any material, so when I apply tensile force, so the force what we are going to apply here is only tensile force. When you apply a tensile force, if you apply it continuously, so there won't be any crack formation or breakage in that material, but it will be reduced. It will be drawn to a wire. So example is copper wires. So let us consider our copper wire. How we are making this copper wire? So you have a big material. So this material is drawn. So it has been applied a tensile force continuously. So what happens? It becomes a small wire. So when you apply it, the length is increasing. Your length is increasing. At the same time, the diameter of the wire decreases. So higher the diameter decreases, that one we call it as a ductile material, right? So ductile material is something like this, shown in the figure here. You can able to see. So mainly a material. So copper material is having more ductile property, right? So I can able to see something like this. So it can be drawn into a wire. So a continuous force is applied. So without any breakage, that will reduce to a wire, right? That property we call it as a ductile property. Next is malleability. So just opposite to ductile. For ductile, we use tensile force. Whereas for malleability, we are going to use compressive force, right? For example, gold coins. Consider a gold coin. So gold is having more malleable property, which means I can hit a gold, I can compress it as much as I can without any cracks, right? So you can able to die a casting or something like that when you apply it. So without any cracks formation, you can able to reduce its size, right? So that we call it as a malleable property, right? So now you can able to understand copper and gold. So I can't say that gold will have more ductile property, right? Similarly, I can't say that copper will have more malleable property. So it depends on application where you are going to use a particular material, right? So next, you will proceed with brittleness, a material which breaks when you apply a force. That material we call it as a brittle material, right? Example is glass. If I consider a glass, even a small amount of extra force will, let me consider it's like an impact force. When you have an impact force, then what happens? That glass will break, right? So that material we call it as a brittle material. The next one is toughness. Toughness is the ability of a material to absorb energy, right? So for example, if I apply impact load, so something like this, let me consider. So you have a steel rod. So with the hammer, if I hit the steel rod, so if it is a brittle material, it will break. If it is a tough material, it will bend. Instead of breaking, it will bend. So it will absorb the energy. Whatever the force we apply, it won't deflect that much. So it will absorb and it will consider it. So it can withstand. That material we call it as a tough material. So next is hardness. So this plays a major role now. So everyone, I think everyone is having mobile phones, and you are heard something like gorilla glass, something like that. So which is scratch resistance, right? So if you have a property, right, which is very rigid and it is resistant to pressure, so that material we call as hard material. All our mobile phone screens is having some gorilla glass, something like that. They call it something like that. It means it is very hard. So there won't be much crack. So there is no formation of scratches. So that is why we call it as a scratch resistant. That property we call it as a hardness property. You can able to see. So how to test this hardness is, so you can take a particular material and you can scratch by using some files. We can able to identify. That is one way. Other way is there are some hardness missions. There is something called as viscous hardness, Rockwell hardness missions. So these missions is used to identify what is the hardness of a particular material, right? So based on the hardness, you can able to classify. So you can use that material for a particular applications. The next is missionability. So most of the material will have a missionability property, which means any material which can be missioned easily, right? So whether it may be a turning operation, so what you have done in lathe, or it may be a hammering operation, or rolling operation, or sheet metal work, whatever it is, if you can able to made it as a particular application, you can able to machine it, then we call that material property as a machinability property. So this is another just a GEF file of identifying what is your hardness test. So there are two ways of identifying it. One is indenting. So you can make an indent, you can identify. So large indentation is less hardness. Very small indentation is high hardness. That is one type. Other one is you have another way. So you can able to see it's like a grinding process. So just grinding it. So like a same load. So one is having grinded more, the other one is grinded only less. Then whichever is having lesser grind, then we call that as a hardened material, right? So the next one is a rigid material. So when a material withstands less bending, then we call that as a rigid material. It is also related to stiffness category. You can able to see here, right? So when a same weight is applied, one stainless steel is bending, whereas a fine ceramic alumina is not bending. So bending is very less. In that case, that material, so the fine ceramic material will be more rigid when compared to the stainless steel material. So a stress is something which is resisting a force, right? So anything which resists a force, we call that as a stress. For example, so let me consider, I am going to give you some work, right? You are not doing it. What happens? We will be getting some stress. So because you are resisting, that resistance we call it as a stress. So similarly, for any material, when you apply a force, the material will resist for the force applied. That resistance we call it as a stress. So let me consider here. So here you can able to see a load is applied here. It's a tensile type of load. When you apply it, it won't come directly. Inside there will be some resistance. So that resistance we call it as a stress. So normally there are two types of stresses. One is a normal stress, other one is a shear stress. The formula for stress is force by cross-sectional area. P is what I call it as a force, is applied here. A is a cross-sectional area. Cross-sectional area is perpendicular to that force. So force is Newton, area is meter square. So Newton per meter square or Pascal, we can call it. That will be the unit for your stress. So the next one is stress will be a tensile stress or a compressive stress, whatever the load is. Here you can able to see load is acting towards outward. Here the load is acting towards inward. Right? Both we call it as a stress, and the formula doesn't changes. So it is always force by cross-sectional area. So let me consider here. So let me consider this is a cylinder. So your force is P. Cross-sectional area is area of this circle. If you consider here, force is P and area of this square, right? So cross-sectional area will be a square, right? So you have to identify the area perpendicular to a force, right? That is very, very important. This is another one. So stresses are applied only for straight type of beams. So when you have a bend beam, something like this, when you apply, so you may have stress as well as moment. You have a combination of these two, right? So we call it as an eccentric stress. So you have stress force and of course a moment which will make the object to bend. Next is shear stress. So previously we discussed about force by cross-sectional area. Here force by parallel area. So stress is applicable in parallel to your force, not perpendicular to your force. Next we will go for strain. So stress is something like resisting the force. Strain is just opposite. For example, today I have given one problem, tomorrow I have given two problems. You're trying to completing it. Day after tomorrow I am giving three problems. I am increasing my problems. When I do that, you will get strained. So you can able to see. So there is a biological term, something like this, eye strain, which means you are watching TV continuously. You can say that your eye is strained, right? Similar to that, the material is also a strain. So how to identify the strain? Let me consider this figure. You have an object with an area. When you apply a force, your object is deformed to a particular distance. So previously it is L. Now my new object after applying force, my object is L plus del L. So the del L is extra deformation. This del L divided by my original length L, we call it as a strain. So strain is change in length by original length. So if we use a symbol epsilon for a strain, so this strain is equal to change in length, which is extra part, divided by original length L, right? There are different types of strains. So longitudinal strain, lateral strain, shear strain, volumetric strain. What am I discussing here is a longitudinal strain, right? So force is applying here. So change in length by original length. That is my strain. So there is no unit for strain. Okay. Right? So now let me show some examples. Right. One is like this. Here, material is like this. When you apply a force, you have a force P. My stress is P by A, and my strain is change in length by original length. Let me increase the area. So my cross-section area is twice. So when you have 2 times the cross-section area, which will be more benefited? Stress or strain? Stress value. So my area is larger. Since my area is larger, the stress value will decrease. Since area is in denominator, my stress value will decrease, right? But there won't be much change in my strain. Now, instead of length, I am giving higher length, right? This is my original length. Now my length is twice. Which will get affected? Stress or strain?
Strain.
Strain. Yeah, very good, very good. So strain is getting affected, right? So in this case, because my length is more, when length is more, my deflection is also double. So your main problem will be in your strain, right? It won't affect your stress. So it should be, so why I am showing this slide is, so as an engineer, for example, if you have an application, you are doing some analysis, you identify that your stress is more. In that case, what you have to do, you have to concentrate on the cross-section area. You have to increase the cross-section area to reduce your stress. If you identify your strain is more, which means you have to reduce the length of the particular material so that your strain will be reduced. You should know, based on a particular application, which one has to be increased and which one has to be decreased. To identify what is the particular property for this, we will go for stress strain test. So this one shown here, we call it as a universal testing machine. So material, whatever material it is prepared as per ASM standard, right? So based on standard, it is prepared and it is marked at a particular point, a length L, and it is applied in this, and they will be testing it. So when you test, you can identify what will be the value for stress and strain under different loading conditions. This is the stress strain diagram. This material, whatever here, is for a low carbon steel, right? Low carbon steel is mild steel. That means my carbon percentage is less than 0.15. So it is very, very less. So we can use this type of material for most of the cases. So because it is very ductile material, but it is very corrosive. If I consider here, you can able to see you have a straight line, a small dip, and then it goes something like this to the top, and then it ruptures, right? So you can able to see here. So at the top you have ultimate strength, so maximum load it can withstand, and below that, so you have sigma y, you can see below this 40. So that is your yield strength. Up to that, you can able to see my line. So my graph is linear. After that, it is non-linear, right? This property, so up to a linear line, we call that as an elastic type. So after it goes off the linear, it goes for plastic stage. After a plastic stage, it gets failed. There is another one. So here you can able to see here. So this is aluminum alloy. Aluminum is also having similar type of curve. Only difference is you don't have a dip. So instead it is somewhat straight. But again, you can able to see it is a linearly variable. So you can able to see it is linearly varying. If I analyze this, so the material, you can able to see there is a test specimen here. So you can able to see there is a dip. So this one we call it as necking. So necking will occur only for ductile type of material. So before it fails, it forms necking. It's at a particular location, you will get this necking. So when it fails, you can able to see how it breaks. So there is a small neck type of arrangement. So always an engineer will choose ductile material, right? They won't go for a brittle material because they can easily identify. So if there is a small necking formation, so large deformation is produced for a ductile material before it fails. So it is better to go for ductile material rather than brittle material, because for a brittle material it is not possible to see something like this. So next slide, I will show you how a brittle material will be. Yeah. So you can able to see here, when it breaks, it is flat. It doesn't have any neck formation. It is flat. So this material will be a brittle material. So if I refer my stress strain curve, you can able to see the curve will be like this. It goes straight and suddenly it breaks. So we can't identify so whether that point is a maximum stress or something like that. It is not possible for a brittle material. When you look here, so you can able to see the second diagram. Whatever it is shown here is tensile type of load. So for a tensile load, you have a sudden rupture. But when you consider a compressive load, this is similar to your ductile material. You have an ultimate strength and then it breaks. So a brittle material can withstand more compressive strength rather than tensile type of load. So consider a cast iron. So you can able to see an anvil which is kept in the workshop. I think you have used that. So for any punching your name or something, we use that anvil. So anvil, it is made of a cast iron. It is very, very brittle material. So it can withstand heavy load. All are compressive types of loads. So whatever we hit, it can withstand. Similarly, concrete floors, whatever concrete we have, that also deals with brittle material, which is having high compressive strength rather than tensile strength. So you can't consider glass, right? Glass is what I can say. So it depends on the thickness of the glass and other property. So I have to identify whether it will withstand high compressive or not. Okay, but most of the brittle material can withstand high compressive strength rather than tensile type of loading case. But this is not same for ductile. Ductile, it will be different. So next, so we discussed about elastic behavior. So elastic behavior is something here. So up to this. So for example, if I consider here, up to this, you can able to see its a line is linear. Sorry, I think here. So up to this, your line is linear. Up to this is elastic. So which means up to this load, if I release it, it comes back to its original position at point A. It doesn't have any strain formation. So which means as we discussed last class about rubber band. So at a particular, so let me consider a 10 mm rubber band. You are expanding it for a particular load, releasing it. Again, if the rubber band is having same length 10 mm, then it is on the elastic stage. What happens is, if I increase my rubber band load, so suddenly, let me consider, I am applying load up to point C. Now, if I release it, instead of 10 mm, the rubber band will have extra 13 mm. 3 mm will be extra, right? So instead of 10 mm, the length is increased to 13. So this 3 mm is here. So this is the 3 mm. So A to D. So A is 0. Additional 3 mm is deformed. So this we call it as strained. So which means my rubber band is now at a plastic stage. It can't come back to point A. It is not possible because you applied more number of forces. So for elastic material, your strain will always be 0. Whereas for a plastic material, when you cross that elastic limit, when you go for plastic limit and you apply a load, there will be a small deformation, right? This leads to failure. So always as an engineer, we have to choose our limit up to this elastic. So we have to design till elastic limit. We should not cross that elastic limit, right? Because when I release it, it comes back to my original position. It is not deforming. So I can reuse it again and again. So there won't be any formation. The next one, is Hooke's law. So Hooke's law states that under elastic limit, your stress is directly proportional to strain. So which means under my elastic limit. So that limit before that, your stress is directly proportional to strain because the line is always linear. So since the line is linear, we say that stress is proportional to strain. So in order to remove that proportional symbol, we will introduce a constant E. This constant we call as Young's modulus. So it is also called as modulus of elasticity, right? So this is the main property for any material. So Young's modulus is the main property for any material. So here you can able to see, I have shown a diagram here. The first one is a pure iron. So you can able to see it's a stress strain curve, something like this, and it ends here. Next is the carbon steel. It goes like this. High strength alloy, it goes like this. Quenched tempered alloy, it goes like this. So you can able to see your Young's modulus. So it is always linear. Lower the Young's modulus, higher the elasticity. If a Young's modulus is less value, which means elasticity is more. Elastic property is more. So that is what it means. If my Young's modulus is higher value, it means elasticity property is less. Pure iron is more ductile and more elastic when compared to the other materials. So because of that, your Young's modulus here is very, very less. So when you go more than that, so your Young's modulus differs accordingly. Now you have a note. So for any material, why we are considering only Young's modulus? Why can't we consider other properties? Why can't we consider strength? Why can't we consider tensile loads or something like that? So the thing is, for any material, right? If you heat treat that material, I hope you know something about heat treatment. Heat treatment is changing the material property a little bit. So what they will do is they will heat the material. So when you heat the material, the molecules in the material will expand and then they will cool in a different process so that the material property will change slightly. When you do these things, your strength is affected. Your strength of the material is affected, but your modulus of elasticity is always same. Young's modulus is always same. Only your strength value will differ. So if I consider a mild steel, we don't know whether it is heat treated or not. So I can't judge mild steel with the strength. So if I judge mild steel with the strength, it means that there may be an error because the mild steel may be heat treated, which will decrease the strength or increase the strength. So, but when you look after it, your material, your Young's modulus is same. So mild steel is a material which is having the same Young's modulus. So we are using that for calculation purpose. We'll go for some formula, what we discussed. Because about two formulas. Stress is posed by cross-sectional area. Strain is change in length by original length. So now we discuss one more formula, Young's modulus. Young's modulus is stress by strain. Okay. So we identify what is the formula for change in length. So you know Young's modulus is stress by strain. So Young's modulus, stress is force by cross-section area. Let me call P by A. My strain is change in length by original length. So I will put it in the equation. So your Young's modulus is equal to P by A divided by change in length by original length. So I have to know what is my change in length, right? So my change in length will be, so E is equal to PL by A into del L, where del L is PL by AE, where P is the force, L is the length of a particular material, A is the cross section of the material, E is the property of the material. So for any object, you consider any object, even a rubber band, if you know the property of the rubber band, Young's modulus of rubber band, if you know what is the load you are applying, if you know what is the length of the rubber band, and if you know what is the cross section of the rubber band, you can calculate what will be the change in length produced on the rubber band for that particular force. So change in length can be calculated by using this formula PL by AE.